was going into the computer settings. So what we set on one side is kVp, on the other side is MAS. MAS is MA, which is our milliamps, and seconds. So together that makes mass. We just kind of call it mass. We don't say out MAS every time. For the kilovoltage side, that's our dial that's telling us how many volts we want to come through. We call that kV. Essentially, it truly is our kVp, our peak kilovoltage that the machine is going to allow to come through the circuit. So kVp and mass are our two settings that we're setting effective on our control panel before we do any exposure. When we're setting that, we're telling the machine how many x-rays we want, and how much energy we want them to have. So by setting our factors, we're trying to balance for the part we're x-raying, the energy that's going to go through it, how much is going to get through to the image receptor, and how much is going to be absorbed in the bones or the body, and then how many we need. That's going to give us two things on our picture when it comes out and we look at it. How dark it is, and how many shades of black and white and gray we're going to see. So we're going to get into that later in another class, but the shades is by the penetration, by how much energy we give it, how many photons make it through, and how many get absorbed. The number is how many photons of each energy level we're making, determines how many photons hit. The more that hit, the darker it is. And then we have new stuff with digital where the computer fixes it for you. So kVp is the energy. That's going to give us approx, in theory, the shades of gray. The number of photons is the mass. That's essentially how many photons we're going to make of each energy level, how many photons we're going to make it through. The higher we go, the more, the darker. The more photons make it through, the darker the image is. So if we do way, way too much, it's going to be too dark. If we do not enough, it's going to be too light. We say other things affect it, but we say kVp is our controlling factor for one thing, mass is our controlling factor for another. We know if we bring our tube distance in, or if we use more kVp, more photons are going to be more penetrating, so that's also going to affect darkness. It gets a little confusing. I don't want you to jump ahead yet to thinking about that, but I'm just telling you what it is. We got a whole month to get this straight, and this chart in the back, these arrows up and down, the back of your book, kind of talks about it too. But we haven't gotten there yet to what you guys need to know for any of this.
On the PowerPoint slide, it's got like quality and quantity.
Yep.
So which one?
Yep, good. That's where we're getting to. So the video yesterday actually talked about this, just a smidget, a little sentence. kVp is the energy level or the penetration of the beam, how many wavelengths we're going to see, how short or long they are. That is the quality of our beam. He goes with the quality of the beam. Mass is the quantity. The number of electrons we're going to boil off gives us the number of photons that are going to be made. So mass is quantity. Another word for quantity, he said in that video yesterday too, intensity. That gets some people confused. What is it? Intensity. So intensity is how many? A lot of people's minds want to think intensity is the wavelength and the energy. It's not. How many photons, how intense the beam is how many photons. So the intensity, that's quantity. That word is somewhere in the chapter when you read. So quantity and quality, that's our two ways we describe our beam. The quantity is how many photons, the quality is how much energy it has, how penetrating is it going to be. So,
the quantity is how many?
How many photons? How many X-ray beams are we making? So once we select our factors for our part, the tube's going to heat up on one side and make our number of electrons boil off that we set, and it's going to give us the energy on the kVp side for how much energy, how much attraction do we want to have them slam in and make our photon be that wavelength. Now, remember that chart with the bell curve he showed? That was the different energy levels in our beam, because our beam's not one energy level. Kilovoltage peak is the peak energy that the volts are being applied. Hello? So, here, this is for you.
Is that his?
Yep.
Oh, that's, go ahead, sit down, that's what I wanted. No, Eric, come on up.
So the peak energy, KVP, that's our peak potential difference we're applying for the electrons to slam across. The energies are going to vary from 0 up to that maximum KVP that we applied. So our beam is not one energy level, it's a bunch of different energies. Depending on the potential difference we select, the KVP that we select is going to how much attraction the electrons are going to jump across the two. So that's going to determine our penetration, our energy level of the beam, our quality of our beam. The mass that we set is the quantity, how many photons we're going to produce, how many electrons are going to be boiled off.
Love those electrons. Don't be like an electron, be positive, not negative.
So two things happen at the target when those electrons hit it, and that's the first thing on chapter 6, page 62. Characteristic interactions and Bremsstrahlung interactions. That's what this whole chapter is about, those two main interactions. So when those filament electrons come across, they're going to hit the atom target. We know the target is tungsten, so we're thinking about a tungsten atom today. Tungsten atom is made up with that atomic Z number of 74. So it has a lot of things going on in it. That's why it's a strong element that has that high heat capacity, high melting point. It's a very strong metal, and that's why we use it. So we can hit it with electrons all day long for years before we wear away the metal. So when we're thinking of the atom, there's a picture of it in the book, a couple pages over. On 65, there's these shells coming out from the center of the nucleus. So back in chapter 2, that little atom that I had for you guys to look at, I wanted you to know that the nucleus has what in it? Anybody remember or know? Not negative. It's positive. Something like that. So protons and neutrons. Good. I heard it over here. So protons and neutrons are in the nucleus. Then it has these rings going out around the nucleus where these little balls on it. Those are electrons. They're negative. So in the middle, our nucleus is tightly bound, positive protons and neutral neutrons, and then electron shells coming out until it meets its makeup of whatever the atom is, and in our case, it's tungsten, so it has lots of shells with lots of negative electrons floating around it. And the drawing is drawn out flat. Remember, atoms, they're more, now scientists have decided, they're an oblong shape, and they're all spinning in different rotations. All those little rings and shells, they're not flat, like we see it in a picture. So when we're thinking of the atom, when we're having electrons from our anode side, when the electrons hit it, they have a possibility of interacting with any of those shells in the tungsten atom. So we're talking about interactions on the atomic level when we're making our X-rays today. I know, it's crazy. This is the physics part of class. So the first interaction I'm going to talk about is characteristic. Characteristics are going to hit and interact with this one specific area. So when we're looking at the atom, look at the red ring around the center of it. There's only 2 negative electrons in that center one. That's called the K-shell. And we looked into this as to why it's called the K-shell. It's not in the book. When they were, whoever was developing the atom Bohr's model of the atom is Bohr, I don't know if it was him. I'm pretty sure it was now that I'm thinking of it. He did not know if there was going to be inner shells more. So he named that K shell, thinking they might go in all the way to A and find more shells. But they never did. K shell is the very first shell around the nucleus of the atom. There's a rule that the K shell only has 2 electrons in it. The rest of the shells vary to balance it out, and then I think the last one can have a maximum of 8. Not as important, that's the octet rule. Don't need to worry about that. But you do need to know that the K shell, all atoms only have 2 electrons in K shell. And when we're talking about characteristic interaction, the drawing of that with the atom is on page 64. Characteristics mean they're interacting with that inner shell electron. So characteristics interact with the K shell electrons. Bremsstrahlung, on the other hand, doesn't interact with any of the electrons. It comes close to them and produces an X-ray in another way. Bremsstrahlung is a German word. Remember, Mr. Rinken was German, meaning breaking radiation. So if you think Bremsstrahlung, think breaking. Characteristic, we're going to get into why it's called characteristic in a minute, is the electron shell of the K shell. It's characteristic to the K shell's energy. We talk about characteristic. So that's only 2 things that can happen to produce X-rays. 2 different types of interactions, characteristic and Bremsstrahlung. Okay?
You said characteristic involves the K shell.
Yep.
And the K shell has 2 electrons.
Yep, and we're going to draw it in a minute and talk about it more in depth. So if you're not quite there yet, we'll get there hopefully. So the 2 types of interaction, characteristic and Bremsstrahlung, and we're going to focus on characteristics first, because I think they're both pretty easy once we talk about it. So looking at the drawing on page 64, that's the model of what a characteristic interaction looks like. Putting it up for them at home. So we have a center with our protons and our neutral neutrons floating around in the atom. Then we have the K shell. Then we have L, M, and it goes on out and around. We only care about the K shell. K shell has 2 negative electrons in it. Now, we're going to talk about these other shells in a second because something else happens in them. But for what numbers wise, this one's the only one that really matters. There's negative electrons all the way around the atom everywhere. So when an electron comes off the tube and slams into the tungsten atom, and when we draw an electron, we draw it in a straight line because electrons are not a wave. But when we draw an X-ray photon, it's a wavy line because it has energy. So on the drawing, you'll notice there's wavy lines and straight lines. The straight coming across is an electron hitting into the K shell electron. It's being brought over with such force because of that potential difference that it was attracted and slamming into the atom. It is knocking out this electron. It has to have energy enough to knock it out. Kevin, stand up. And Megan, stand up. If Kevin is running as fast as he can, full force into Megan, he's going to knock her down. But now, let's see, 2 that are closer in size. Come on, sit down, guys. Okay, Koala, you stand up. Ashley, stand up. They're kind of close in the same size. So if they're running with the same energy, neither one of them are going to get knocked down. They have to have a greater energy, or in our instance, you can sit down now. for us to have this interaction happen, a characteristic interaction has to have energy of that electron hitting that electron out of the K shell, has to have energy pretty close to it to knock it out, or it's not going to happen. So characteristic X-ray photons happen at the K shell. So on the chart, there's binding energies on page 64, and this is another number you need to know, 69.5. That's the energy of K shell electrons. And that says KeV, kilo electron volts. So if we set our KVP, our peak kilovoltage, the energy level is measured in kilo electron volts of each photon or each electron that's coming across. So we need at least pretty close to almost exactly 69.5 or greater to have the energy to knock it out. So if I set KVP at 70, I can knock out a K shell electron. But if I set my KVP at 50, not enough energy, not going to happen. So no characteristic interactions are going to happen at 50 kVp. 70 kVp, yep, and above, we can have them. Most of our exposures. So characteristics only happen at 70 kVp and above. The only time we're going to knock one out is when it's approximately equal to the value of 69.5. So if we're getting close to that value and that electron comes close to this electron, they're going to get knocked out. So we only have two characteristics each time that could happen.
So if the electron is an electron is coming at the other electron.
Yeah, because these are coming from the filament.
So if that's 69.5, I thought if they were similar in size, that wouldn't.
Has to be approximately equal to or greater to it. So to have it knock it out. Anything below won't. That's what the book theory says. So it will if it's the same. It could knock it out. What it's doing, remember, energy can be transferred. It's transferring its energy into it. And it's leaving what we call a vacancy or a hole here when it knocks it out. When it knocks it out, all that energy is transferred into it and it leaves in the form of an X-ray photon. That energy is transferred into an X-ray. That's when we create our X-ray.
If it's coming from the filament, isn't that the mass side, not the side?
Good question. So the mass is boiling off of the electrons. That is the mass side. But we apply the KVP to the anode, the target. The tungsten target is getting that positivity to attract them into it, to slam into it. So this is our filament electron that we boiled off, coming over, slamming into the target. We're just talking about one of those.
You said the KVP is attracted.
The KVP attracted it over. And depending on what KVP we set is how much attraction it's going to slam into it with.
And when I think of the slamming, I think of the slamming into the actual.
The slant of the metal, the anode angle.
But like this is creating an X-ray right
Yep.
here. This is like one
This
electron
is-
hitting an atom.
This is an atom in the metal,
Oh,
the
in the
tungsten
metal.
atom. These are the atoms, the atomic level of the
Okay, sorry.
tungsten that we're hitting. So when this photon's coming out, it's going to come out in whatever angle. It depends on which way it was going to go, whether it comes down through the port window or up and gets absorbed into the lead. When this vacancy happens, we have something called cascading. The atom wants to be balanced again. So the next closest shell electron is going to jump in. And because an atom is rotating those shells around it at all angles, it's not necessarily this shell that jumps in. Just for the drawing purposes in the book, they use the closest shell to it. So that's going to cascade, that one's going to cascade, that one's going to cascade until they're all balanced again. Each time one of these cascades, they're losing some energy. So a photon is going to be made. These are such low energy though, because they can only lose whatever the difference in the energy is from the shell to the shell. We don't need to do the math or anything. Just know these are lower energy, The one here has the highest energy to lose, so it's going to be a higher energy photon. These are going to be useful X-rays. All of these are not probably going to help make our image. They're going to be absorbed in the skin of the patient and contribute to patient dose. So we do some things later on we're going to talk about to get rid of them. Yep.
Oh, and they had like where the port was, like they labeled it a filter.
A
but they were
filter,
saying,
yes,
like,
to
the
filter
weak-
those
the weak
weak
ones
energies. Yep,
filter
you read
out.
ahead. We're going to talk about that in a minute.
Right.
Yep. So what we want to know about characteristics, number one, they're K-shell electrons of tungsten atom at 69.5 energy level. In order for our electron that's coming over to hit it and knock it out, we need our KVP to be about 70, close to that 69.5 or higher. Anything lower than that, no characteristics are going to be made. You on board now back there, Danielle? Not yet? Kind of. You're wanting it to soak in, I know.
No.
What about at home, guys? You got it? Somebody? No? Not yet?
I'm going to be honest, no, but
Kinda.
Characteristic, we're gonna have you guys act it out too. I always like to see your thoughts on it. We always have somebody be in a car crash or something, cars hit each other and knock them out and spin. Yes. Yeah, first thing of characteristic is it's only happening at the K-shell electrons. I'm gonna write it here, K-shell. And we know that there are 69.5, according to some scientists, that we have the energy level. So in order for an electron that's coming across to knock it out, it has to have an energy equal to or greater.
is it the same for the other ones too?
No. Well, for any of these shells, yes, sorry, yes. But we are only caring about K-shell because that's the energy that's going to produce a good X-ray photon to come through our patient. All these are too weak. So if you look at the chart, you'll see how much they drop as you go down the shells. 12 and then 2 and then 0.6, 0.8, 0.08. So the energy level of those other shells are super low. So not going to help us out with making a good X-ray picture. That's to make X-ray production. So now we're just talking about, we've already made the electrons jump across. So we're talking about how the photons are made in the tube. And this is on the atomic level.
And
So,
sorry.
uh-huh,
And the useful X-ray that comes from that interaction, that's like contributes to that 1% or what?
yes.
And those
Ooh,
other
we're gonna get
ones?
deep into that in a minute. Yep. He's jumping ahead again. Yeah.
Shut up.
So pretty much,
Sorry.
the electrons come off the filament, hit the K-shell. If it's a proper, if it's 70 kVp or above,
Yeah.
then you have that.
Yeah.
You have action.
We have action. Now, is there a chance that that electron has 70 kVp and above and is just gonna pass right by and not hit an electron? Yes. So not every single electron that we make boiling off of the filament is going to be turned into an X-ray photon. 1%, 99% heat. They lose their energy in heat.
If it did the same thing in the other shells, it doesn't do anything.
It does. It's just they're low energy, that energy chart, they're not going to be a productive X-ray. So the only ones we care about right now are characteristics in the K-shell. So our KVP needs to be how much about? Yep, 70 or higher.
Smart, Michael. I like the way you think.
All right, so let's get rid of characteristic and move on to the other one, Brims.
So it can't be 69.5, it can be 69.5 and above.
Yeah, but we don't set
But
that.
you want to say 70.
Yeah, we set 70 on our control panel.
So it has to be 69.5.
Truly, yes, but we don't have that setting.
So
70.
All I'm gonna remember. Kevin just said it.
She said not today.
I know, I'm not drawing a real tungsten atom, I'm just making circles.
How dare you not
I know.
draw it to scale either?
All these are negative. Up in the class, I had the students make them at home, and there's some hanging atoms up in the room you guys were in, you might have saw them. Protons, neutrons in the nucleus. All right, so Bremsstrahlung means breaking radiation. Let me scroll back to Brems. Yep, the other page is Bremsstrahlung, right next door.
You said breaking radiation?
65, yep. So Bremsstrahlung is like you're walking by and you see a really cute guy or a girl and you stop and turn and look.
Yeah.
So here comes that electron. It gets super close to the nucleus. The nucleus has such positivity that negative electron is attracted to it, so it turns in another direction. It breaks a little bit,
That means
slows down, and turns. When it does that, the energy is lost in the form of a photon. That's Bremsstrahlung.
hold on.
Yeah.
Yeah.
So Bremsstrahlung is that electron comes close to the nucleus and has some pull to it because of that positivity. It slows down and turns direction. When that electron does that, that breaking, it's losing some energy in the form of an X-ray photon. Yep. So Bremsstrahlung is an electron coming in from the filament side, slamming, not losing all of its energy like it does in characteristics, because it doesn't interact with anything. It gets close to the nucleus. Depending on how close it is to the nucleus, we could say within this range, it's going to have a different amount of pull, of gravitativity pull. That negative electron that's coming in, it's going to slow down and turn in another direction. And when it does that, it loses some energy in the form of an X-ray photon.
Can I repeat what I
Yes.
just make this right?
Yep.
So it's when the electron goes towards the nucleus, suddenly turns, causing it to lose energy and creating a X-ray photon.
Yep.
Okay. Okay.
Yep. So Brems does not touch any electrons, doesn't knock anything out. It's losing its own energy. That electron's energy is lost when it slows down in the form of an X-ray photon. So if I have 100 electrons coming across, each one of them hitting the target with 2 chances of hitting a characteristics each time, or a whole lot more chances of becoming close to that nucleus and losing some energy. Bremsstrahlung is more prevalent. More chance of this happening than these two getting exactly hit. So we have characteristics in Brems. Bremsstrahlung are more prevalent in the tube.
So the second it loses energy is when it
Is lose energy in the photon. Yep. Yep. I'll find it in the book for you to highlight.
When does which factor?
We have a probability percentage. That's what I'm trying to find for you to highlight.
I like that though.
When do they, you said KBC, do they both happen at the same time?
Yeah, they'll both happen.
So like,
1% makes it to the egg.
So when we're talking about the percentage of X-rays being produced as heat and X-rays, we can say we have 100 electrons coming across. Only 1% are going to be X-ray. So that's 10, or 1, right? 1 X-ray photon. So let's make it bigger. Let's make 1,000. Then we could have 10 X-ray photons with 1,000 electrons. Out of those 10, I can't find it in your book right now.
same.
Does anybody see 75%?
It's still not.
Mm,
No, so it's still the energy.
Okay, here we go. 90%, this is important, are brims. And 10% can be characteristic. So if we have 10 X-ray photons, almost all of them, 9 are going to be brims, only 1. Is that right?
Yes.
Somebody do the math. Are going to be a characteristic. We have millions being made, so we're not going to focus on that. But only characteristic if we have above 70 kVp. If not, then all of them are brims. Below 70, 65 kVp, all brims.
Which makes sense.
Which makes photons, yeah, that we use. Yeah, they're just lower energy.
So if it's above 70, are there any brims?
Yes, 90%. Only 10% are characteristics above 70, no matter what.
So even though it hit nothing and it turned as a nucleus, it still becomes a photon?
Yes. So we're kind of projecting it between here and here, that it's getting attracted. So it's such a pull that it's losing enough energy to make a photon that we would use.
And these
If it's way out here, it's not.
they're both coming from the filament.
Yep. All of our electrons that are coming across in both of these are from the filament
And they happen at the same time.
at the same time. Yep. We don't know for sure, but we know percentage-wise, 90% brims, 10% characteristic.
And being a photon, that means as well being an X-ray.
Yeah, photon is an X-ray.
And nothing
Yep.
determines which one's coming out.
Not really.
Okay. You say like what creates.
We only know for a fact we don't have any characteristics below 70. But other than that, above 70, it's the percentage of the beam. So remember that Bell chart he did? And he had that one little peak by itself that was characteristic? That was the 10%. All the rest of that spectrum, be it Bell, was brims, ranging from 0 to the maximum kVp set.
Okay, so I have a question.
Uh-huh.
I'm trying to understand it in my brain. So it may be a dumb question, but so the boiling electron filaments are hitting, and it almost lands into the nucleus, but it doesn't. So that energy differs and becomes a photon?
Yes.
It becomes an X-ray.
An X-ray photon. They're the
Okay.
same thing. Yep.
Just need to-
Yep. So now I want you to take a sheet of paper and draw out the 2 interactions for yourself on it and write it in your own words. I know you probably did it as I was talking, but write it again.
Can I write it on my notes paper?
Yeah,
Oh.
yeah, just for you to have. I usually have like a printout and have a blank page for you to do that. Writing out what the difference is between the two, drawing the atom in your own words, so you can have it. Characteristic and brims. One is going to hit a neutral electron, one's going to come close to the nucleus and lose.
What is not?
Now, does it make it out of the window? Depending on what direction. Go ahead. You're working. After this, if you want. Yeah.
I'm literally right.
Like a dog. It's nothing extra.
Yeah, I know, straight. I just bring it just in case.
Can you pass me the
Get out, and they're like, oh, I've got limited funds. They're like, oh, no, you're fine. That's because I'm behind the broker. Like, 12 years long.
I like the.
That's like hospital, they go to different take 400 milligrams of Tylenol and 400 milligrams of ibuprofen.
That's what I do.
It works like, it does. It like melts. They knock it out. It's like you have one like one.
If you're hungry and you don't eat, you're like that for a while, right?
Usually, I mean, when you do something, you don't eat. It should be useful.
I don't really eat.
But I usually don't get it because I want to be there.
So it's being attracted to the nucleus and it makes it change direction. So like we said, now you go get one, that's what happens. Exactly.
Yeah. Maybe I pay, but.
Whoa. Well, that's usually me, except usually it seems my bills, like I'll have like a little bit of money to last the next day. But, or I'll got smart, put in another letter that I paid. This needs a raise. This one, got one. And this is the on a paycheck that it showed, but it only showed for 1 week. So I might not know the next paycheck.
Have the money. It's gone. It's knocked out. It's like you didn't. No.
Right. Not today, next paycheck. Saturdays and Sundays, yeah, we're working 12 hours on, from 8 to 8. We are. I'll put it on the group chat. Lots of different
Knocks out that stuff in the group one, and then when that one gets knocked out, consider it being produced.
Do it.
So.
Yeah, right now, because right now they're mostly PRN and part-time, and if you're either one of those, they just work the schedules. They're like, okay, this person can work whatever. And we have one girl that just started, and she. I mean, we work with everybody. There's another girl that didn't have her right now, and she didn't work in September because of their clinicals, because they sent her to Daytona. So there's.
Right.
Like that.
That's the cascade. All right, so we got the 2 interactions. Let's kind of talk about a couple more things that people were thinking when we were talking about this. So page 64, don't forget what happens when that electron is gone and knocked out. There's a hole that has to be filled, so the cascade happens and more photons are being made. So lots of different energies are being produced in a characteristic interaction. With BRIMS, only one photon. One electron doesn't touch anything, loses energy when it changes direction, one photon's made. So characteristics, because of it leaving a vacancy, has the cascade happen. So all those shells that are cascading are making more photons. So we actually have a lot of photons being made with characteristic, many different. BRIMS one photon, because it's that one electron losing some of its energy. So now let's talk about BRIMS a little bit more. I'm going to have you look at some in the book. On page 65, it's telling you a couple of different scenarios. Underneath the red box, critical concept about BRIMS, then it talks about the energy. So we could have a photon coming in at 70 keV. And if it's passing through with that nucleus, leaving it with 30, it's going to produce, sorry, it started out with 100, I guess I missed that, no little problem. It's going to produce a photon with 70 keV. If we had 100 set on the control panel, that electrons being attracted with 100, potential difference of 100. It gets close to the nucleus with a power of about 30. We don't know what the real power is. Depending on how close it is to the nucleus, the more attraction it's going to be. They subtract the difference to give us the photon's energy level. So they say in that scenario, 70 keV will be produced. So when it's coming through, yeah, depending on how close it is to the nucleus, that attraction is going to get a greater pull. So if we set 100 and the attraction here was 30, and when it turns, it's going to lose that. So the photon's energy is going to be 70.
Depending on how close.
Depending on how close it is to the nucleus.
Does anything determine how close it is? Or does it just happen?
It just happens, but here's the math for what you need to remember. And I like to highlight the average energy of the BRIMS photon is 1/3 of the KBP selected. It's right at the last sentence in that first paragraph where all the numbers are, underneath the red critical concept box on 65. So our average energy of the X-ray beam, when we're talking about BRIMS, is 1/3 of the KBP set.
So 1/3 of the 100.
Yep, so 75 about. What would be our average energy? So on that chart, that spectrum chart, that peak, if we were to really look at that video again, it should say numbers on it. This does not. Our book does. That's our peak average energy of the beam, 1/3 of the KBP set. So remember the curve went from 0 all the way down to the highest KBP set, but the high end, not very many are that. The middle of it is the 1/3 usually. And the characteristic is always at 70. So we know that's when characteristics happen. So the peak of characteristic is always going to be 70 on the chart.
I don't get how they would get 20 being average. It's not 1/3 of 100.
but that's just one photon they're talking about. We're talking about the average energy of all the beam when we are doing a exposure. So that's the difference in the math there. Not every one of them are going to be 75, but the average.
So,
Trying to think where's that in my slideshow for you guys.
To get the photon energy, you take the KEP.
Did you guys see that at home on here where I have the FREMS average energy?
So it says it's 70.
Well, 1/3 of the KVP selected. Maybe it's in the end of the slideshow. If 100 was set.
Okay. It's 1/3.
Oh, it would only be 25, I'm sorry. 1/3. There it is. So we're gonna look at those charts in a minute and we'll talk about this more then. I don't know why the chapter's broken up like this. It's gonna talk about filtration first. So remember with characteristics, those photons that are cascading aren't very high energy and we don't want them to affect our patient dose and come through and just be absorbed in the patient. So we get rid of them with filtration in the tube. So the paragraph after where it says 1/3 of the KVP selected, it's talking about those cascading, all those weak X-ray beams. In our tube, and we'll try to look at that today. I can't remember if our tube shows it. It might say it on there. We add filtration in there to filter out some of those photons so that they're not going to absorb to the patient. So we absorb them beforehand with some aluminum and some other stuff. So the collimator has mirrors in it. That kind of filters out a little bit of those X-rays. So we say a total of 2.5 millimeters of total filtration is in the tube. So we add slices of aluminum in the tube before those beams come out and hit through our patient. We get rid of those low energies with that. So the magic number, 2.5 total filtration. So how I like to talk about tube filtration is quizzes. Everybody always wants me to do this at quiz time, if I talk about it like this. But we're not allowed, so don't ask, sorry. But if we were, you would want it, because if we have 10 quizzes, we'll just do 5, so I don't have to write as much. And you get 100 on the first one, and an 80, and then you get a 0, 3, because you weren't here or something. And then you get a 70 because you missed a lot of information, so you didn't do good on the next one. 1, 2, 3, 4. And then you get an 85. Anybody want to average out 180? Eight, 16, 17. I'm getting 24. 245. Did anybody got a calculator? Yeah.
I'm pretty sure it's 23.
Okay.
16, 23, yeah.
Okay. I was putting another one up top.
3.
Divided by 5. Ooh, that's a 40 something, isn't it?
You're not, math, because if it's 23, you have to do 2 plus the 1, so it should be 335.
Oh, okay. That sounds better for an average. Okay. Ooh, that's still not a good average, right? 67. So what if we drop 1, get rid of that 0? Our average is going to jump up because we're only going to divide by 4. So that's what happens with our average energy of the X-ray beam. If we have filtration in there, we get rid of those low energies, those low numbers, so our energy of the beam average goes up. So filtration helps us with our beam quality. Our energy level of the beam is our quality of our beam, our wavelength, our penetration.
Say it one more time.
Yep. So filtration helps our beam quality, our energy of the beam, our average energy of the beam. So if we have 5 X-ray photons, these are really long wavelengths, short wavelengths in the middle, And then really, really long ones from those cascades that aren't gonna do anything but absorb in the patient. And we're gonna get rid of those with filtration. So now if we had numbers here, we could say our average energy of the beam is better, more penetrating, higher energy is left. So our average energy of the beam increases with filtration.
Yeah, like I put this thing.
Yeah. So we like filtration in the tube because it makes our beam better, higher quality, more penetrating. Higher energies are kept, lower energies are gone.
Average energies of the increases.
With filtration. So if we get rid of all those low energy characteristic cascades, we would be left with just the friends mostly. I think where it says it in the book for you to highlight it, I think it's under the critical concept of filtration on 66. Added and inherent filtration removes low energy photons.
Do we need to know the difference?
No, just know the total number amount of total filtration, 2.5. Because every tube's going to be different. They're going to add filtration in there to make it match up to the 2.5.
I don't really get the 2.5 though. That 2.5 milliliters.
Millimeters.
Oh, that's just a thickness.
Of filtration, the thickness.
Okay.
But we don't put straight aluminum at 2.5 millimeters of thickness because we have inherent filtration in the tube. The collimator, the mirrors, and things like that filter out too. So total is 2.5 millimeters.
Oh, so just, yeah, so the collimator factors into
Into
the
it.
2.5.
Yeah, that's the inherent. Yeah. So in the tube, inherent plus added aluminum. So total filtration. It just says it improves image quality. Compensating filters is something we're going to talk about next. So inherent tube filtration is helping us get rid of low energy X-rays made in the tube. That's the whole reason for it. Compensating filters are the next type of filters we can have, and they're added to the collimator or to the patient, and there's two pictures of them on 67. There's a wedge filter that's hooked onto the collimator in that picture, shaped like a triangle, half wedge, a slice of cheese, slice of pizza, something like that. And it's thicker on one side and thinner on the other. So this does something similar to what the anode field effect does. It makes us have high energy on the thin side and lower energy X-rays on the thick side of the filter. So look at the foot. The toes are really, really thin, not a lot to them, but the heel and the arch of your foot getting towards the tibia and the fibula where your leg is and your calcaneus, all that's really thick. So see how the high energy waves are coming through the thick part, the low energy photons are coming through the toes. So with that thick wedge that we added, that filter, it's getting rid of some of those energies so we don't burn out the toes. Have I ever used one? No, never seen one at the hospital. But hey, that would be great for if I wanted to get an even exposure of my foot to not have my toes be super dark and my other part be super light. You could use a higher energy beam, filter out those high energies where we don't want them, let the high energy beam come through where we do want it. So that's what a compensating filter does. It eliminates some of the photons where we don't want too many. So it reduces the quantity, the intensity, it reduces some of the number of photons. And it's reducing, on the thick side, high energy photons. Where the aluminum filter is going to reduce some of our photons out of the way. The other type, letter B, is the boomerang filter. Never seen this either. Would like to use one, but I've never seen one used. It's under the shoulder. So the outside of our shoulder is really kind of not a lot, just a little bit of skin. But over here we have a lot of muscle and the scapula behind it. Where the joint space actually is, it's hard to penetrate. So we need to use a lot of KBP to get through that. But over here we have a little piece of bone called the greater tubercle. If you move your shoulder in and out, you can feel it rotate, little bump. that gets burned out. Because we have to use so much KVP to get through the shoulder joint to see in here, we can't really see the bone here. So a boomerang filter, you put it under the patient's shoulder, it absorbs some of those high energy photons from here, so we don't have the burnout of the greater tubercle. Supposedly, like I said, I've never used it. Yeah, it would be nice. So generally speaking, we adjust things on the control panel with the computer now, or we just have a really light shoulder joint if we need to see over here, if this is the area that's hurt. We don't use a high penetrating beam, so we can see that area. Digital, so much better, you guys, than film. Film, you would have to have this light, we call it a hot light, you hold the x-ray up to it and try to see the area that's too dark.
If it's thick, don't you want the higher energy beam to penetrate?
Yeah, but the other parts, little thin piece of bone, it's gonna be burned out, too dark, because we use too much penetration. So that's what the filters do, they help even out the uneven body parts for the beam. Boomerang filter, wedge filter, two types of filters. Filters are on our objectives that you have to know about, they're on the registry. So you wanna know that these are filters that we add either to the collimator, or we can put them on the patient to filter out the beam to get rid of some of those high energy photons to see the part better. Two types of compensating filters that we have, wedge filter and boomerang. And that's on page, what page was it? 67. I don't think I have a picture of those on here for you guys at home. Now today, Miss Osteen is going to have her class come talk to you guys about some chest anatomy. I had on the PowerPoint the hip anatomy. I will print that out and we'll go over that tomorrow afternoon after our exam. And while we're doing that, we're going to go in the dark room today and learn about the processor and processing film, so we can start doing some exposures next week, hopefully. I don't know if we'll get to do any tomorrow after the exam, we'll see. The other part of this chapter is talking about quality and quantity. Do we need a break first? Yeah. And then we'll come back and talk about that. I'll check in with her, see what time she's gonna come up. Is that clock not working still? Let's see. So don't worry about this. So let's come back at 45.
Deal.
Good.
So it's 9:34 guys on this clock, so 45 after.
Okay.
10 minutes.
Bad share.
Neutral. She's right. Negatives are the electrons on the outside.
Is it positive and neutral or just neutral?
Time to go to
Positive and neutral.
Oh. How long did you say? 10 minutes?
Yes.
45.
45 after. Quarter till.
Hey, Shari. Picking up what you dropping down today?
It's too much. I'm like falling for the.
I was like, I'm gonna watch the video. BMO.
For my X-ray medical tape, you have to take this same thing, even if you already so. So I'm gonna be coming back.
This is just like my first topic, is Adam.
Yeah.
It's my first topic. It's in this class. Sarah works every day for you.
And
Background.
oh, background.
I'm like, okay,
We need some fresh air and a mask break.
Oh, I didn't know where you went.
I had so many things I wanted to say. I had so many jokes lined up.
You know, I just wish that was it for the day on that. I can go back and learn yesterday.
But wait, there's more, but wait.
Study more.
And,
I need to start my outline so I can.
yeah, like with all this, I kind of forget what the beginning of the chapter is.
Right. And if we're right, and I just looked, and I mean, we still have a decent amount, we're only halfway done, she said.
Oh, the history. People dying. Footnotes,
Where's lunch at today?
your house.
All the way over there. I think I might have a one box of bagel bites.
I know you did. I know you keep Lunchables up in the ceiling.
There's some Lunchables over here.
maple flavor.
Okay, I think it's another one.
Alrighty, so we're gonna look
That's
at
good.
the last part, which is the spectrums. I
So
hate
this
the
is the
spectrums.
whole chapter, the whole thing? Okay, 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 okay. Got you.
So you don't like what you're about to.
Yeah, I don't really like them that much. I hated them in school, the charts and all. But some people are more visual and it makes more sense seeing it in the chart, so we're not gonna have a lot of this on the test, but
So we're starting with
the spectrum,
emission.
emission spectrum, yep. But before we get to that, we're gonna recap on beam quality, because that's where it takes off in the chapters. So after the filters on page 68. So page 68 has the little chart.
Mine's not. I feel like let's start.
Yeah, page 68. So yeah, it doesn't go with the PowerPoint. No.
Okay, we're good.
Yeah, you're good. Page 68 at the top. This little table is going to be a good thing to know if you understand why these things are happening. So page 68, look at that little chart at the top. Factors affecting beam quantity. It's a little green, table 6.2. Oh, you got a different one.
Yeah, it's okay, I got it. Right here.
Okay, I forgot about that.
Okay.
So if we're talking about quantity, what are we talking about? Quantity in the beam,
Math.
okay?
The number
The
of
actual what quantity is, number of photons.
photons.
Yes. Things that affect that. Number one, if you increase your mass, which the chart says if you increase mass, increase quantity. More mass, more heating up of the filament, more electrons being made. More electrons being made means more electrons slamming into the target, which means an increase in number of photons. So that one's easy. Mass, if you want to write beside that, is our primary controlling factor for quantity. I'm going to write it on the board. Mass is primary controlling factor for quantity. So for how many photons we're going to have, the quantity of our beam, mass controls it. We want to double the amount of photons we make, we double the mass. It's a directly proportional relationship. If I select 5 mass, we're just going to say, we don't usually use 5 mass for a lot of things. We're not equal to mass to how many photons we're making. We're making millions, 5 photons. If I select 10 mass, 10 photons. So I'm doubling the mass, I'm doubling the photons. That's just the concept. So mass is our controlling thing that we use to control our number of photons we make. But other things, you kind of already know a little bit, can affect the number of photons. kVp. If we increase the energy of our beam, we're increasing the penetration of the beam. So we're going to make more photons be able to come through the part. So kVp is going to affect the number of photons that make it through.
And when you say increase in kVp, does that mean the pull
Yep.
from the cathode is stronger?
Yep.
So,
Yep. So increasing kVp. Yep. Yep. Increase kVp, as the chart says too, increases quantity. Increases the penetration, because a higher energy beam is going to be more penetrating to go through a part than a lower energy X-ray photon. So an increase in kVp affects, now I'm writing it kind of small here, quantity. If you increase kVp, you're increasing the number of photons just because we are changing our beam penetration, our energy level of our beam. Because kVp controls our energy or our penetration of the beam. How much energy are we going to have those photons come out with? Higher kVp, higher energy. kVp is not like mass though. If we double kVp, we're doing a lot more to our energy, so we're not equally doubling the number of photons that make it through. But kVp is not making more electrons. kVp is just making a stronger pull of positivity to the tube, to the anode. Mass is making the number of electrons, the milliamps, and then the seconds is the time, the S. So distance. If we increase our distance of our tube, that's inverse square law. Not as many photons are going to make it through the patient. So it's going to decrease our quantity. So an increase in distance decreases our quantity, making it through to the IR.
Increases are what?
Yep. So look at the chart. Increase in distance decreases quantity.
Increase distance, decrease
Quantity.
quantity.
And these are talking about making it to the IR through the patient. Yeah. Further away, not as many are going to make it because they're going to spread out more inverse square law. Increased filtration. Adding more filtration decreases the quantity, takes away. No, you're thinking of annoyed hill effect?
Yeah.
We're talking about adding aluminum or putting a filter on there is gonna absorb some of our bead. So adding filtration is talking about that.
Oh, okay.
So increasing more aluminum or adding a filter. Decreases quantity,
That's just taking away the actual.
taking away some of the bead.
Say it one more time.
Yet increased filtration decreases quantity.
Balances out the exposure.
Yeah, but it helps us, we want it sometimes, to get rid of low energy photons, to balance out the exposure to a part. Yep.
And one thing back with the mass equals control, increase in quantity.
Uh-huh.
When you have the S there,
Uh-huh.
are you talking about the increase in
Yeah,
seconds?
seconds. So MA is milliamps and the S is for seconds.
So to have the increase in quantity, you have to have the S as well, or just milliamps?
What is MAS?
Yeah, that's what we use to set on the control panel. So they're talking about our, yeah, we don't have filters at all the clinical sites. I've never used a filter.
Oh, we got another sheet.
Yeah, but we need to know.
Because it's more advanced now, that we don't, that you are not familiar with the filters
Hold on.
and the.
Too many people talking in the back. Hold on. What's your question?
You said that you haven't used a filter. Is that because it's now more advanced? They don't use that? Or-
I've never seen a hospital have a filter used. What's your question about?
No, I was just trying to understand where the filtration came in, but
Uh-huh.
they explained it, what you just said, you just something added, but is there also filtration already established?
Yes.
Yes, the port.
In the tube itself, there's added and inherent filtration that's in the tube. We add aluminum in there to equal the 2.5 millimeters of total filtration. And the reason we do that, to get rid of those cascading low energy photons that are coming out of the tube, so they don't get absorbed in the patient. That's the inherent total filtration, inherent and added. So that's automatic in the tube. We don't do anything with that. It's just there. The ones we can add are the compensating filters, the boomerang or the wedge. So any type of filtration, just know you add filtration, take away quantity.
So back to the mass.
Yeah, let's talk about this mass thing again that he's wanting to know. We haven't talked a lot about what the S is. So we talked about MA, that's the amps that we're setting to heat up our filament. The second part of that, the S is seconds, that's for how long. So we use two things when we're setting our controls for mass. It's a second controller and an MA controller, two dials. Yeah,
Is that what you selected yesterday to make it?
a longer exposure so we could see it light up for longer.
If you have it at like 6, you said that that's normally, that's not what you would.
You wouldn't do that long of exposure because it overheats the filament and might burn it out. So we don't want long exposures too because of breathing and motion in the body. Motion is bad in X-ray. It blurs things out, like you're taking a picture of somebody trying to run or a car driving, it's blurry. That's what happens to our structures in the body. So we want the short time so we don't burn out our tube and we can have less motion. But we have to set something because we have to set what we call mass. So MA, milliamps, times seconds equals mass. So I'm just going to make it easy. If I select 50 MA, sorry, got it right, big A, at 1 second, that's 50 mass. I could do 25 MA at 2 seconds, still equals 50 mass. I could do 100 MA at 1/4 of a second, 0.25. Should that equal 50 mass? I hope I did my math right in my head. Wait, 50, 100, this would be half a second, sorry. Still gives us 50 mass. So multiple combinations of MA and time can give us the same amount of x-rays, same quantity. They're all 50.
Yeah, I was just thinking along the lines of, like on an exam, if it's asked, does milliamps cause an increase in quantity, just milliamps?
Yeah, so if I don't adjust my times, then no. We have to think of it as mass.
So
We have to know both to
mass-
say the number, the quantity. But if I keep my time the same at 1 second, and I go from 50 MA to 100 MA, am I doubling the amount of photons? Yes, because I'm doubling the mass.
Therefore, you're doubling up the amount of electrons being made.
Yes. Yep.
But you have to have time.
So I can either heat it up hotter, that's our current, or I can do it for longer, boiling off more. So either one. Altogether, we have what we call mass. That's our number of electrons we're boiling off, 50, 100, whatever we set. We usually set 2.5 mass for a hand and like 12 or 15 mass for a chest. So just to give you an idea of mass range. Abdomen, something really thick, maybe 30 to 50 mass. So not big amounts of mass.
So mass the number of electrons being boiled off.
It is essentially in the tube. That's what we're doing. We're boiling off a certain amount of electrons.
And increasing the amount of beams.
Yeah, because therefore those electrons are going to get turned
Because if
into
you want to
X-ray
do something
photons.
safe, you need more.
Yeah. So mass is the number of photons we make. KDP is the energy that we give them by the potential difference that we attract them over. Starting to click a little bit. So lots of things can change the quantity of photons coming through. Mass controls it. We always use mass as our controlling factor for how many photons we're making. But we always have to keep in the back of our mind all these other things, the SID, the KDP, and filtration, if we add it, is going to change the quantity. So those are the main things right there in that chart that can change the quantity. That's it. So if I ask you, well, that we can do to our tube, patient part thickness is going to change it, so I can't say 100% that's it. Because if I have a thin part or a thick part, they're going to absorb the x-rays differently. A football player's shoulder or a little skinny person's shoulder, they're going to be different absorption. So that's why we change our factors depending on the body part we're x-raying. So beam quality is always talking about the penetration. Quantity is number. The quality, before I go into quality, what's some other things for quantity that we could have on a test question maybe? Quantity could be number of photons or number of electrons. How many? And then that magic word that everybody gets confused, intensity. That doesn't seem right, I know. The intensity of the beam is the number of photons in the beam. How
I just
many?
think of like a lot of people.
So, you say that the quantity can be the number of photons and what?
Am I saying it wrong? Number of photons equals the number of electrons. Essentially, the number of photons we have are directly related to how many electrons we boil off.
But the only thing that's different is what's a good.
Yeah, is it going to be a useful or not useful photon? Yeah.
So when we go to X-ray, we have to gauge someone's size and determine the mass based off of like how big they are.
Yep. Yeah, it's in here too.
Yeah, can you do it by like weight or height or any of that?
Somewhat. We measure part thickness. We have calibers that we measure to do that, and there's charts that you can look at. But you get really good at just knowing, looking at someone and knowing.
I mean, there's probably like a couple numbers that you can use, like.
Most X-ray.
Yeah, there's ranges. We'll give you guys the ranges in positioning class for the part.
Right.
Now, do we go outside the range occasionally? Yes, but
Most places have a chart.
most places have a chart for their range.
If it's like a bigger patient, you just bump the number of
And you're gonna love this. We have computers now. You push a chest and it gives you the mass and KVP for it. And you're like, why did I need to go to X-ray school? I can just be a button pusher.
In school, I literally thought
So it's kind of like in the military, when we do land nav, we need to know.
Yeah, when I got my
Yeah.
second
Now
extra
there's
done, like she
electronic-
did everything, like she did all these little things on the computer. And it was
I was
like,
like, I'm gonna have to do a formula every
I know, you don't use the
out
formulas.
there, and they're like,
No.
oh, we have a chart right here that shows.
So-
you look up like chest.
All the stuff they make you know and then you really don't need to know it. All right, page 66, I just want you to highlight something on the quantity before we move on to quality.
66.
Second paragraph on quantity, underneath quantity. It says beam quantity for you looking for it in your book. It's the bold word under beam quantity. Okay.
So it's 65.
So quantity is the number. So if beam quantity varies, ooh, this is a little bit confusing, by the square of the ratio of the change in KVP. If KVP is doubled, the intensity, the quantity, increases by a factor of 4. That's the inverse square law. Yep, quantity of X-rays changes by an intensity or the square of the distance when we're talking about distance and KVP.
Is this just saying we need to know the inverse square law, or?
No, this is a whole different formula. This is called the 15% rule. So as we go on,
That is the N square.
that's what we learned yesterday. So this is kind of a different formula we're going to talk about. Yep. So beam quantity is going to change by KVP. If we increase KVP, this is just saying that we're doubling KVP. The intensity is going to go up by 4. So you don't need to worry about that part. You need to know this 15% rule part, the next part. Yeah, she's like, I wish. I'm not going to have 15% roll on our exam, guys. I'm just wanting to tell you about it now. It's going to come later. We have a whole other day when we talk about this. It's in this chapter though, and I wanted to get in that word intensity there, meaning quantity. So you have that. Yeah, it has to do with inverse square law, but
Just the mean quantity variance.
yep. So for math, if you're good at math or you want to use the calculator, you can up and down multiply out by 15%. But if you're like me and don't like math, here's what my teacher told us. And it almost works almost perfectly. It's like 3 to 5 KVP off. Changing KVP by 15% is essentially adding or subtracting 10. Up until 100. When you get to 100, then you got to go to 15. 100 plus 15% is 115. But 70 plus 15%, I think, comes out to like 82, 83. I don't know. Get a calculator if you got one close by.
You said adding or subtracting, you said 10%?
It's 15% is the rule. So it's a 15% rule. A change in KVP by 15% essentially changes the energy of the beam so much that twice as many photons go through. So it's like doubling the mass without doubling our mass. So sometimes we use it to do just that. We want to make the beam more penetrating so we get more photons to come through. So that's the 15% rule. If you go up 15% in KVP, you're getting twice as many photons to come through because we're making their energy go up. Everything else stays the same. Now, we got another rule later on in the next physics class called the maintaining density rule, the density maintenance formula. I think they're going to change it to exposure maintenance because they took away the word density. But that's to adjust your factors, and you won't need to learn that in my class. So we're not going to go there.
You said we don't need to know.
Not for the test tomorrow. We'll get into 15% rule more later. I just wanted to talk about it because it's here in the chapter, and also because that's where the word intensity, if you want to highlight it, intensity is the quantity.
But everything we're talking about today, other than that, is going to be on the test.
Yes.
Okay.
Yep. And I'm not having emission spectrums on the test, but we're going to talk about them.
Or no emissions.
So now quality is penetration. So different energies, wavelengths is going to change the amount of energy the beam has, how penetrating it is. So when we're talking about quality, we're talking about the energy of our beam. How much of a quality beam do we have? How penetrating is the beam? So energy, penetration, trying to think what else. The wavelength, whether it's shorter or longer. Usually we just say energy.
Yeah.
So on a test, if we're talking about energy or penetration, we're talking about quality. If we're talking about quality, talking about KVP. Increase in KVP increases the quality, increases the energy, increases the penetration, increases wave, decreases wavelength, makes it shorter. But because of that penetration, more are going to go through. So it does increase. It affects the quantity. KVP does two things. It affects our quality and our quantity. Primary controlling factor. So we have primary controlling factor for quality and quantity. For quality. That's what we use to control our penetration or our quality.
But the primary controlling factor for quantity
Is mass. Yes, Eric.
KVP affects our quantity and quality, right?
It does affect it. Yep. It's controlling our energy though, controlling our quality.
So the primary controlling factor for quality is
KVP. KVP. Test question. What controls quality? KVP. What controls quantity? MAS.
Say that last part again?
What controls quantity? MAS.
KVP also affects it, but it's.
Does KVP affect the quantity of photons? Yes, because more penetrating equals more making it through to the IR. Yes.
Sorry. So, the question.
What affects quantity?
Yes.
Yep. What controls quantity?
KVP.
Quantity. Mass. Controls quantity.
Is there more penetrating means
Yeah.
more what?
Huh?
More penetrating
More penetrating, higher energy.
means more photons to the ion?
Yes. More photons to the IR. So this one is more energy, shorter wavelength than that one. This one is more energy than that one. So this one could be 50 kVp, 70, and 80. Higher number, higher energy, higher potential difference, more higher energy photons were made. With 50 kVp, only brims. 70, brims and characteristics. 80, brims and characteristics. 1/3 of the energy is the average energy of the brims X-rays. Characteristics X-rays energy is always 69.5. That's the energy lost. So brims are the range of X-ray energies. Characteristics are always going to peak at that 69.5, and we're going to look at that on the spectrum in a minute. So we know what quality and quantity are. There are two things that we talk about when we're talking about our beam. Our quantity of our beam, how many are in it, and our quality, what's their energy level? How penetrating is it? So now the emission spectrum, I think we're ready for it. One more table. The one that changes quality. Only two things there. KVP, that controls it. Filtration. If we add filtration, we're increasing our quality because we're increasing our quiz average and we drop some of them low ones. So we're getting out low energy, increasing our average energy of the beam. So increasing KVP increases quality, increased filtration, increases quality. Both of them are together. So I'm just gonna go over a few of the charts. There's different things that these are used for, mostly to tell you about the energy of your beam, and if you change something, where does it shift on the energy level? So let's look at the first one. This one just says a little graph from 0 to about 90 kVps where it ends, the red line. So it's on page 68 at the bottom. I'm going to erase this so I can draw it up here. 68 at the bottom, the little chart. It's a little pink colored line in the book. I don't know if it's different in that book.
Nope, you're fine.
Okay.
Pink and purple, but the line and then there's like a hump.
Yeah.
Sure which one you're talking
So we have this spectrum going like this. And we have the level 0 and then 100 at this end. And then it slopes up and comes down and then stops just before 100. So I'm kind of guesstimating that that's about 90.
Right. You say the emission spectrum is on the test tube, right?
No.
No.
I won't have any of these graphs. So they are to help understand some of the stuff we're talking about though.
Right.
So we have this graph, mine's a little bit more of a bell than the one in the book, but this is considered the brims. And then there's a peak right around where that line is drawn. 69 is characteristics. So all of the rest of the spectrum is brims. So this line right here is where characteristics would be. So whatever level, what's the other side of that? Number of X-rays, 0, and it doesn't really give us any numbers. But these are number of photons. So we'll just say at this peak is 100, just because that's where this one ends. And down here is 0 photons. So at this level here, we don't have any photons at 0. But what's that? Probably 70, 75 or so. This 50 is probably here. And then at 100 photons in this range right here of energies. So if that's 69 energy, that's 100. Down here we don't have any at 100 energy. So most of our photons are here. So I would say 50 to 69. Energy level number-wise, KeV, kilo electron volts energy. So an average of our beam is 1/3 of the kVp set. So if they set almost 100 or 90, our average should have been about 75 or 25, sorry. So maybe my number's off here.
At that peak,
Yeah,
what's happening at that peak right there?
that's just most of our X-rays. So remember, this is the number of X-rays here. So yes, the middle would be the average. So about 25, 50.
So these are the X-rays, not the electrons that
Correct.
absorb.
No, these are just the average of the photons, the energy level of our beam. That's what the emission spectrums are all about. So we know characteristics are 69. What we're really looking at is the brims, the range of energies for brims. Yeah.
So what's the average KeV?
So in this chart, it's going from 0 to about 90, with the peak being a little bit after 25.
Okay.
So if you set it at 100, your middle should be 25.
Whenever we do test on this, they're using our version.
Yeah, I don't even know if we'll ever test on these emission spectrums. I gotta go back and look at the registry and see if they're on there. But these, what I'm looking at for you guys today are a couple of these specific charts to show you how they shift when we change things. So we're gonna look at that now. Look at page 70, the chart that says change in milliamps. So we have a green line and a pink line. Again, I'm thinking pink. 200 MA, 400 MA. Our number of X-ray peaked up because we doubled the MA. But the energy didn't shift that much. The KVP didn't change, just the number of photons. So by changing mass, you're only changing the number of photons. That's one good thing. Mass doesn't affect anything else. Mass is only the number of photons. AVP is tricky because it can change a couple of things. Kilovoltage peak is the next chart, from 72 to 82. See how the shift just moved a little bit? The peak, the number of X-rays went up, and the shift of the average energy moved over a little bit between the two charts, the two pills. So by changing our energy, we changed our number of photons, because more photons can make it through, higher KVP, and we changed the higher average energy of our beam because our KVP was higher. So that's what we're looking at on the charts, what changes and just these little things can do. We're not going to look at phases and generators because that's in your next class. Adding tube filtration at the bottom chart, from 4 millimeters to 2 millimeters. More X-rays made it through with less filtration. Adding filtration is reducing the number of photons. So the graph for 4 millimeters is low on the numbers, high on the 2 millimeter. Also, the energy changes. Adding filtration moved our green one over to higher energy because adding filtration increases our test score, our average energy. So our average energy of the beam moved over and went up. That's all I'm looking at these spectrums for, is to show you the graph for people that are visual to see what we're talking about.
There's a table that shows.
Yeah, I like the table. See, I like that. That's how I learn the chart. I don't do the graphs too much, but they do show it for people who are able to learn that way. We have these charts in books in the X-ray departments, but we don't ever look at them. I don't think they're on the registry. I have to double check the registry list again. But emission spectrums, if you do need to read them, that's what they're wanting you to interpret from them. Changing KVP, what does it do? Increases the number of photons, increases the energy. Both of those move over. The quality and quantity. Yep. So the table on the last table kind of puts it all together. Generator type is something we aren't looking at right now. That'll be in your next physics class. So after lunch is when we're going to go to the lab.
When are they coming in the top?
That's when they're coming. Because we're going to break out into groups, because they have not been in the dark room yet either. They were online for this class before, and for their 1000 class, they didn't come in and do any of the online stuff. So we're catching them up on that stuff. They only got to come in for positioning classes. So you guys, front table, you're going to group together and show us a Broom-Strong interaction and acting it out. So you guys can meet up in the front or in the middle circle here. You guys in the back. Hey, hi. You guys, I'm going to have you in 2 groups. This half and then this half. You're going to do 2 sets of characteristics. Or you think you can all do it? Yeah, that's too many people. I think that's too many. You guys are in the library? Yeah, we're in the library. We're going to make up each other the photon, the nucleus, yeah, and then they come up and demonstrate it, a characteristic interaction. You guys work around.
Are you the thing that swerves or always swerve out?
I want to be the thing that goes like these, and it goes all like.
Are we being recorded?
Like, I can be coming up to you and I'd be like, what's up, Jess? You'd be like,
Then I need Michael to be that.
you'd be like, you stop. Coronavirus.
Hey, Kevin.
Shit is getting real.
Yeah, we got enough people, you can all be a different electron shell.
So we're all gonna have
Every day, yeah.
Well, that means you just need
Can I get filtration and I'll be like, you cute, you're not, you cute, you're not, you Latin, you're not.
You're doing characteristics, all of you. if you can get everybody to be a part of it, if not, you can do 2 separate characteristics.
The electron on the facial.
I think if you make everybody be, one person be a photon from each shell, you'd have enough with all your people.
Negative electron.
You guys at home? You can watch.
We're not hitting. We're not hitting.
I'm moving you over this way because they're gonna be acting it out in a minute.
Oh, yeah.
Yeah.
I want to be this person.
You want to be that person?
This is Jeff. So then, hold on. I'm perfect. All right, so then who's the nucleus? All right, let's be 2. Let's do 1 here and 1 here.
We need
So we
somebody.
swirl around and we don't hit them.
Somebody to be the photon.
Yeah, somebody needs to be the photon.
And then someone needs to be this little thing.
I'll run off. So I'll be behind Kevin. And then whenever
Jess is the initial.
So Jess is the initial, Jess is the initial thing, and if somebody can be.
That's okay, I'm gonna all this.
You can, there can be someone here that like distracts you, like forces you. It's like,
I don't want you guys to get really into it and they go to knocking into each other.
You'll be that. You be the one that I get distracted with.
Okay, what do I do? Wait, what do I do?
you're over here and you're like trying to get her attention. And then.
So what is it?
That could be me and Twilight, yeah. And then Michael can be the photon X-ray.
Yeah, photon X-ray.
Okay, right now, yeah.
So, as soon as she goes, skirt, you just wander off of it.
Yeah.
Slither.
So, okay. Jess is gonna approach.
I'm gonna go like this.
You're gonna barely miss
You
me.
should knock me out first. Exactly. Exactly. It goes right. You didn't play. Stay right there.
And then when you get close to him.
I'm just gonna
And then you, yeah, Tanya, you're gonna be the photon, right?
Yeah.
And you guys are gonna be moving.
Wait, do we move?
Yes, you're the electron.
There you go.
Are you gonna do the hand, you know these little things that go like this?
She's the electron.
Well, no, I have to go away.
Yeah. So you have to look like you're going toward him.
Do that then.
And then you're like, oh.
Oh.
And then we will.
And Michael, because you're the photon, you could like go running out the door.
Yeah. High energy play.
High energy.
That's why I said he should be the little arm thing.
You have to like tag. You have to like, because you don't create until
until I mark it. So you gotta like hide right here.
Or,
And I'm gonna go in front of
or
you.
you can just follow behind her and when she spurts, you just.
Yeah, you like
Swear right behind you. And I'm like, oh. That was not good now.
Oh, yeah.
I'm gonna use my life as an example.
Yeah, you're just like wife right now.
And then this will hook on.
Yeah, but this is me and then this is my best friend.
That would be cool.
You got, hey girl, I like you, like, bitch, this is my friend.
No,
Yeah.
I didn't keep getting.
Nope. Is it important that she goes this way? She doesn't need to go around.
Oh, no, chair and spun them around and push them.
When she's coming, when she's gonna, this is the new one. She's gonna go like this. She's gonna go around the other.
Either doesn't matter. She can come close. I can come close and then just be like, just kidding.
So she can go in front.
Yep, anyway. Yep, this is attracted to it. I'm probably.
You try. You try it.
So I'm walking in the middle of how I feel about it.
No, you're just hiding, and then the energy goes off after the fact. So when I
So you're
swerve,
going this way or no?
I'm gonna start coming from.
So yeah, just come off from
I'm
there.
gonna come off right here.
Yeah.
So once I go to her, you just pull yourself off.
Okay, I'm confused.
Follow her.
Okay, I will bounce down like you were.
What you can do to go invisible.
Oh, here.
Come up to him and he's like, oh, what's up, girl? And then you're like,
Hide behind the curtain.
I do, but I like it how like I'm like really about to be there, and then I'm like,
Higher energy when she's closer to the nucleus.
Yeah, so she was close.
I just swerving.
you guys aren't together?
No, she said that you should break a crotch down and run. He's not part of it.
He's not invented yet.
She is not invented. He is still chilling.
He's potential.
I was gonna say, you know what, you should be like,
Your potential
you
image
should act like this is your boyfriend, and then you're like, oh.
Which is kind of what I'm kind of doing.
Oh, but in reality, isn't the main thing.
Okay,
Really,
you can come with her, because you're essentially her energy getting lost.
That's okay.
But we're just gonna pretend because for adult,
Okay, yeah,
purposes
you're a
of these
single
two making
electron.
sense.
I was just saying, you guys are going to the bar, and then you're like, first.
You get but then it doesn't occur for the new person.
It does curve, but at the same time, that it doesn't like give that full effect of I'm exactly like I'm busy. So for that purposes, we are attached, but like you just go over there.
She loses that energy because she.
But I'm gonna be happy that I'm leaving.
Okay, okay. No, because as soon as I do that, we're not fighting because we like each other. I'm gonna swerve away and I do. He's gonna be upset. He's gonna be upset. I'm leaving and he's gonna go like this.
Actually, I have a side piece.
But I have to be so our high energy, but you're gonna be higher energy when I.
But I'm gonna be mean.
His madness got him so far.
I won't be saying it. We'll just kind of like hook arms and then he'll distract me at first and then she got my attention and wins and he's just gonna be like.
Now he's not liking his character.
Well, you started it. You're high energy, but you're gonna be higher energy as I'm losing because you are my.
But I don't wanna go away like.
Then you should have squatted down.
Somebody suggested cry.
Exactly.
Just run away.
It makes it hard.
Maybe you're just her friend for support. You were her wingman that got what else that she could do.
Friday, right? Remember how your brain was off? He's like, oh.
Exactly. That's the way you think.
My grandma would do
For what we're doing with the guy and the girl, it has to fit in perfectly.
Are you guys ready?
Can we go first?
I think so. Stay right there, that's fine, but we'll move you over here unless you want to stay over there to it. All right, you ready?
I still like our other way better, but it's okay. You can walk.
So what is this? This is gonna be a Brimstrong interaction, so we're going to a bar, I think. Or somewhere, a dating place.
We like this version. Me and Michael have decided.
Okay, we'll explain it, I guess, afterwards.
Oh, I gotta go out the door.
Oh, okay, I was trying to get our attention, not be so loud.
Yeah, sit over at the edge, and then you have to, here you go. Then you have to look progressive too. Okay, stand over there. We ready?
Action.
do it.
Heidi's all ready to find her a date.
She's going to
She's
Kevin.
losing some energy. She got attracted to him, but then she saw her and the energy loss in the form of a photon here. Okay.
He's so nice.
I've never seen anybody do that. It's all right, guys. You can do it back there if you're in your places, or you can come up here and rearrange. More spaces up here.
It's our turn.
Hey.
Y'all do a great job.
Not as Beatrice.
We appointed people in the
Characteristic has lots of cascades happening. Oh, okay.
I'm a very penetrating. One of their places.
So ones that don't have signs, they're gonna be our photons, right? You guys?
Oh, she did take it.
No, your cascades.
Okay. You're, so you have to be over here. Oh, wait, we're not.
I was told she's there because I'm taking her place.
So she's an outer shell electron.
And I'm behind you because I'm outside.
Okay.
There's just too many people for us to do.
I know, it's fine. I'm trying to make sense of it too. You guys are floating electrons out here. All right, so who's the photon that's gonna be made? Okay, we got our two photons.
All right, ready?
You're negative.
I'm turning into pro.
Oh, you're gonna put.
Ready?
You get it when we like go off?
Yeah, so you're gonna play two parts.
Yes.
Okay, gotcha. Okay, gotcha. Ready? Here comes electron coming in from the filament. Knocks out K-shell. Cascading happens. Photons are coming off in K-shell and all cascades happen.
Good job, good job.
All right, guys. So after this, we're going up to the lab to look at the dark room. So you guys can try to come back into the lab when you come back on campus, and I'll show it to you. That's it for today.
Okay, bye.
Thank you. Have a good day.
Bye.